So folks, today we are starting up at the top of page 6 and we'll be finishing the last lesson of the unit, which is just exponential and logarithmic applications. This section is important because up to this point it's like, yes, logs, we're solving exponentials, it's super fun and dandy to do, but it actually does have a lot of real world applications to population growth, population modeling, and also with finances. Yes?
Did we already take the 8.3 homework?
We have not. So folks, we have two different equations that we're going to be using in this section. One is exponential growth and the other is exponential decay. Now, we've talked about growth and decay before on the very first page of our notes. Exponential growth was when we had a base greater than 1, and exponential decay was when our base was between 0 and 1, or some sort of decimal or fraction. So exponential growth functions and exponential decay functions. For the left side of the equation, we have a of t, but you can just use y. So a of t or y. And what that represents is just the value after time t. So after some amount of time, how is our population exponentially growing, or maybe how is something exponentially decaying? The A stands for your initial amount or starting amount. So starting or initial amount at time 0. So your A value is actually your y-intercept, which seems a little bit weird until you think about how an exponential equation works. Folks, if I plug in 0 for t, what's whatever this is, 1 plus r raised to the 0? What's anything raised to the 0? 1. And then 1 times our A value gives us our A value. So, that's why your A value ends up being your y-intercept for these graphs. The next key feature is R. R is your rate as a percent is usually how it's presented, but in order for us to use it in the equation, we have to change it into a working decimal. So folks, how do I turn 50% into a working decimal? If I wanted to take 50% of something, what would I multiply it by? 0.5. So if you can remember this relationship, that's going to help you with some of the tougher percentage problems they like to throw at you for the ACT. For example, they'll be like, oh, 0.3%. And this will confuse students because it's like, hold up, it's already a decimal. Do I need to do more to it? And the answer is yes. Anytime you have a percent, you always have to move the decimal point 2 places. So if you can remember 50% is 0.5, move that decimal place 2 places to the left, move that one 2 places to the left, and that would show me that 0.003 would be the working decimal for that percent. So the only other variable here is t. That is your time. And just put a note to be careful with your units. So how is something growing or decaying exponentially after a certain amount of time? On the test, I think I'm going to give you these equations, but you will just have to know how to use them and which one to use. If you're looking at those going, they pretty much look exactly the same, you'd be right. The only difference is that growth functions, we add 1 to the rate, and decay functions, we subtract. So growth plus, decay minus. So we're going to go ahead and to start making sense of this, we're just going to start applying it in this first problem. The first U.S. Census was conducted in 1790. So there's our time 0. Because at that time, the initial population or the starting amount was 3 million-ish. So that's going to be our A value. That's our starting amount at time 0. Since then, the U.S. population has grown by approximately 2.03% annually. That sentence tells us 2 key things. First, it tells us that this is a growth situation, and it also tells us the growth rate. Now, as soon as we see that 2.03%, we are automatically going to change that into a working decimal. So moving the decimal point 2 spots to the left, 0.0203. So that's what we're going to use as R in our equation. Now it says draw a graph showing the population growth of the U.S. since 1790. We're not going to get super fussy with this. What I want to go back to is just what we did in the first part of this unit. What does an exponential growth function in general look like? So first, what type of asymptote does an exponential graph have? Horizontal or vertical? Horizontal. The logs, the trees have the vertical asymptote, so this has a horizontal asymptote. And a lot of times if I'm thinking about growth, I think about the population of bunnies. We have a few bunnies, a few more bunnies. Suddenly, oh my gosh, there's so many bunnies. So that's just a good rough model of what exponential growth looks like. Now part A says to create an equation to model the situation. So this is where we are going to use our formatted model from up above and plug in the items that we know. So as I said, you can use A of T if you want, but I'm lazy and I think it's easier to just use Y. So we're going to go ahead and start with our Y equals. And since it's a growth function, we're going to use A times 1 plus R raised to the T. So since it's growth, we use the plus sign. And now we plug in the things that we know. Well, Y is just going to stay Y. Now our starting amount, A, is the 3 million, yada, yada, yada. So 3,929,214. And then 1 plus 0.0203, and then raised to the variable t.
Michaela McFadden, please come to the attendance office.
So we're simply replacing the variables in the model with the stuff that we know about this problem. Now, your last step would just be to simplify this equation. If you're like, there's not really much to simplify, Ms. Cairo, you're right. The only thing we can really do is add the 1 and the 0.0203 together. So 1.0203. And that would be our growth model. Now, does that satisfy our original rule about growth function? Is the base that's attached to the variable greater than 1? It sure is. So that's why we're going to find it's 1 plus for the growth functions. That will always give you a number greater than 1. And 1 minus for the decay functions, which gives you a number between 0 and 1. Any big questions so far? I know we don't love word problems, but compared to what we've been doing with logs, this is a bit more straightforward. The only thing that's a little bit tricky is just knowing which equation to use and figuring out what your units are, especially in the context of time. So folks, we're going to move on to problem B, and it says use the equation to estimate the population in, let's go ahead and skip 1900. There's already kind of a lot in this problem. It says use the equation to estimate the population in 1950, 2000, and 2050. So let's start with what does this question want me to find? use the equation, all right, that's this guy that we just defined, to estimate the population. What variable is representing population? The y, or your A of t, the amount after a certain amount of time. So we want to find y. So estimate the population, find y. Now if you're like, all right, these are years, so maybe I'll just plug in 1950 for t. Why is that not going to work? Back in the original problem, we let time equals 0 be 1780. So if t is 0 for the year 1790, not 1780, what do I need to do to figure out what I will use for t for 1950? We need to figure out how many years since 1790 this is. So we can't just plug in 1950 because in this model, our t is years since 1790. So if 1790 is 0, what will 1950 be? Well, let's go ahead and take 1950 minus 1790. And we see that we get 160. So t is 160. So go ahead and get out your calculators or grab one off the cart. And we're going to show that for the year 1950, we changed that for our time to be years since that starting year. And now we're going to plug it into our equation. So we go to our model, we carefully type in 3,929,214 times 1.0203 raised to the 160. And this should give us the y value, or the population, if this keeps growing exponentially. And we get a large number with a little trailing decimal on the end. Now, folks, if we're talking about population, do you think we're going to carry that out to the hundredths place for 0.11 person? No. We're going to round to the nearest whole number, and we're going to follow our rounding rules. So I go one place past the place I want to round to. Is 0.1 enough to bump us up? Nope. So that would be our final rounded answer. So 97,896,586 people. And now we're going to do the same thing for a different year. Let's see if I can get a different color here. So for the year 2000, first we need to figure out how many years since 1790 that is, our time 0. So 2000 minus 1790 will give us 210. So t is 210. So we took the year 2000, said that the time since that starting year was 210, and now we're going to plug that in for t in our model. So this is a good opportunity, since this was kind of annoying to type in, and we're going to be typing it in multiple times. It's a good idea to review our calculator key sequence for doing copy-paste. Does anyone remember what it is? Second, enter. Second, enter. is how we copy paste on our calculator. And it will do that for the previous line. So instead of typing all that nonsense in again, I hit second, I hit enter, and now I can override that 160 with 210. Ta-da! And now we get a significantly larger number, but still with a trailing decimal. Now, if I wanted to round this to the nearest whole number, is 0.6 enough to bump us up to a 4? Yep, 0.5 and above bumps us up, so only the 3 bumps up, nothing else. Bless you. So that would be 267,400,294 people. So in that year, that's what our population would be. See if you can calculate the final one. What is our T, our time for the year 2050, and what would the population be following those rounding rules? Our T is 260 for the year 2050. We plug that into the model. And let's see what we got for rounding. Is the 0.3 enough to bump us up? No. So we get 730,392,344 people. So again, folks, a lot of times populations will grow exponentially. Do you think Waukee is growing exponentially? Yeah. Graduating classes have been getting just huger and huger exponentially. This happens when you start building more houses, building more Hy-Vees, building more high schools. Things start to blow up exponentially. Now, do places keep growing exponentially? Not always. Sometimes we run out of room to build new houses. There's just no more land to keep building houses or building apartment complexes. But maybe a better example is animals. So let's say we've got a deer population and it's growing exponentially. What's going to happen before we are overrun by deer? What stops the deer from growing exponentially forever? Hunters are one. Third block said people driving too. If there's too many deer running across the road, there's probably going to be more of them getting hit. A lack of adequate food. As you start having a bigger population, resources start to run out. Also, the more animals you have living in a close condensed space, a lot of times viruses and diseases spread more quickly, or the population of the predators ends up rising exponentially to meet it. Saw a coyote once on Southeast Alice's and University. Have you guys ever seen a coyote around here before?
Saw this one this weekend.
Did you really? Yeah, I thought it was a dog, and then I'm like, oh, that is not a dog. So a lot of times exponential growth is good for short-term populations or things like humans where it's like we're kind of the alpha predator here, so we don't really have to worry about the coyotes and things like that. But a lot of times it's only good for like short-term predictions because after a certain amount of time, a lot of times they'll start to experience some sort of limit to that exponential growth. So just to put it in context of this is important. It is something that they use to model growth in data. That's how we knew, hey, we're probably going to need to build a second high school with the way population's increasing. So this kind of data does matter because you can't just like build a high school in a day. So folks, let's go ahead and take a look at number 2. We got a cup of green tea. It's got some caffeine, 35 milligrams of it. The average teen can eliminate approximately 12.5% of the caffeine from their system per hour. Create an equation to model the situation. So let's see what we have. Is this going to be growth or decay? Decay. Why? Because we are eliminating the caffeine from our system. So this is what tells me decay. So that means for our model, we are going to use y equals a times 1 minus r raised to the t. So for decay, it's a minus between the 1 and the r. So that's what model we're going to use. Let's see what we know. A cup of green tea contains 35 milligrams of caffeine. That is our starting amount of caffeine in our system. So at time 0, we've got an initial amount A of 35 milligrams. Then we can eliminate the caffeine at a rate of 12.5% per hour. We are going to change 12.5% into a working decimal by moving the decimal point 2 places. And again, folks, if you're like, oh my gosh, I'm having a brain moment, I can't remember whether I should move it to the left or to the right, think about 50% being 0.5. That's always what I tell my students for the ACT. It's an easy one to remember, and that will help you remember which way to move the decimal point. So R is 0.125. So let's put this stuff into our model. Y is 35, our starting amount of caffeine. And then 1 minus 0.125 raised to the t. Final step is to just simplify what's inside the parentheses. So y equals 35 and then 0.875. Does this match what we said about decay functions the first day of this unit? That the base associated with the exponent should be between 0 and 1. Is 0.875 between 0 and 1? Yup. So that's why when we're given these rates, these percentages, it's 1 minus for the decay, 1 plus for the growth. So there's our model. Hooray. Part B, use the equation to estimate the amount of caffeine. So we want to estimate the amount of caffeine. So what part of the equation am I looking for? The y, or the a of t if you want to use that notation. So the amount of caffeine in a teenager 3 hours after having a cup of green tea. So what are we going to use for our t here? Consuming the tea is time 0. If we want to find out how much caffeine we have after 3 hours, what are we going to use for tea? 3. It's 3 hours since we drink the tea, which was time 0. So t is 3, easy enough. And then t is 5. So we're going to use the equation 35, whoops, not divided by, 35 times 0.875 raised to the 3rd power. And let's go ahead. Let's go ahead and practice our rounding rules, and let's take it to the hundredths place here. So we'll say y is equal to 23.44, but we look at the next digit to see if it bumps us up. Is 7 enough to bump that 4 up to a 5? Yes. So 23.45, what? Milligrams of caffeine. So as always with story problems, make sure you include your units. Second enter, put in a 5 for the time, and rounding this one to the hundredths place, we've got 17.95. The third digit is a 1. That's not enough to bump us up, so it stays 17.95. Milligrams. So that is some of the applications of exponential growth and exponential decay. We have an additional model that we use oftentimes in finances. And those of you who go on to take finite, we do a lot of stuff with this equation. This is a special type of growth function because if we're investing money, do we want our money to decay? So when we're talking about financial institutions, typically we just want, our money to be growing exponentially. So compound interest is a special type of growth function, and it looks like a lot, but it's actually very similar to the equation above that we were just using. That A is the amount of money after a certain amount of time. So money after time passes. The P. Does anyone know what you call like the starting amount you invest in an account? It starts with P. It's called the principal. And the principal is just a fancy word that we use for the starting amount when that starting amount is money. So that is the same as your little a from above. Now, instead of just 1 plus r, like we had for the growth functions above, we have this dividing by n and then raised to the n times t. Older calculators, make a note. You're going to have to make sure that you put parentheses around n and t when you type that in for the exponent. So if you're using one of the older, chunkier calculators, you have got to put in these parentheses. So older calcs use parentheses. So the 1 plus is the same. The raised to the t is the same. It's the dividing by n and the raised to the n part that is a little bit different. So let's go ahead and define what n is. N is going to be equal to the number of times the interest is compounded in a year. So the number of times the interest is compounded in a year. So if I said the interest was compounded monthly, how many times a year is monthly? 12 times a year. If I said it's compounded daily, how many times per year would that be? 365. And if you're like, what about leap year? We just use the 365. What if I said compounded weekly? 52, good work. It took me a while to memorize 52 weeks in a year. So 52. Now what if I said annually? How many times per year is annually? Once. What about semi-annually? Semi-annually and biannually mean twice a year, so that one's a little bit trickier. But typically, that's going to be what your N is given to you as. It's how many times it is getting compounded. So we've got an investment account that pays 4.2% annual interest. Similar to before, we are immediately going to take that interest percentage and change it to a working decimal. So 0.042. It is compounded monthly. So our N will be equal to 12. 2,500 or 2,500 is invested in the account. What will be the balance? How much is in the account finally after T years? So 2,500 is invested initially. That's going to be our P. And we want to know the balance or the Y value, sorry, the big A value on this problem. The dollar amount, the A value after T years. So part A, we are going to just plug in our variables into that equation. And actually, I'm just going to start by practicing writing that equation first. A is the amount in the account after a certain amount of time. P is our principal, or the amount invested initially. And then 1 plus R over N raised to the NT. N is the compounding periods, and then T is the time. So for this problem, we would be looking for A. Our principal is the 2,500. And then 1 plus our rate, 0.042, divided by 12, raised to the 12t. And gross. Now, similar to above, we are going to simplify what's inside the parentheses. And if you're like, I don't think it's going to be very friendly, Mrs. Carl, let's just see how unfriendly it is. So 1 plus 0.042 divided by 12. Not too horrible, 1.0035. So A equals 2,500. 1.0035 raised to the 12t. Beautiful. So it says use the equation to calculate the account value. So we're looking for Y. How much is that money going to be worth? Sorry, looking for capital A or Y. After 3 years and after 25 years. So for this, it will be T equals 3. 3 years beyond when we initially invested the money. And for this one, T equals 25. Folks, can I distribute that 2,500 into that parenthesis and simplify this even more? If you're like, well, we haven't done it so far with any of those A values or P values, so my guess is no. The reason why we can't is because that 1.0035 is tied to the exponent. PEMDAS says we have to handle the exponent first, and since I can't evaluate that variable power, I can't do that before I multiply. So there's no way you can distribute that 2,500 in, and that's going to be important once we start solving equations like this. So let's go ahead and type that equation in on our calculator. 2,500 times 1.0035 raised to the 12 times 3. I want everybody to try typing that in, just because older calculators, I want you to practice putting in those parentheses. Around the 12 times 3. Or if you're like, I don't want to do parentheses, Mrs. Caro, then just multiply 12 times 3 to give you 36 and just write that as the exponent. That's viable too. So that's what we get. Now, if we're talking money, 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 what place do you think we should round to? The hundredth place. 2 places past the decimal because that makes sense. Get it? Sense. All right, I'll boo myself on that one. $30 stole my recorder. There we go. So boo, yes. So we are going to round it for the unit that makes sense. So $2,000. $835.08. So that's what A is equal to. So the 1 isn't enough to bump us up. So that's our amount after 3 years. Second, enter. And now being careful, because I already had someone today try to replace the 12 with 25. We want to replace the 3 or the year with 25. And that will give us our other dollar amount of $7,131.04. So 3 new equations, but kind of not really, because we've been dealing with growth and decay functions. We've been dealing with exponential equations. So getting comfortable with the variables is the biggest part, and then it's just kind of plug and chug on your calculator. So let's go ahead and turn the page. And wow, 2 problems left of Unit 8. Woo! Let's go ahead and read through number 4. A $1,000 investment is made in a trust fund at an annual percentage rate of 12% compounded monthly. How long will it take the investment to reach $2,000? So I'm just going to start by writing that equation from the previous page. A, the amount, is equal to the principal times 1 plus the rate divided by the compounding periods, raised to the compounding periods times the time. So there's our setup for this one. How did I know I was going to use this equation? Because it was talking about compounding and money. So we've got an $1,000 investment. That's how much we invest initially in the account. So what variable am I going to put that in for? P. Then it says at an annual percentage rate of 12%. So our R will be 0.12, changing that to a working decimal. So 100 times 1 plus 0.12. If it is compounded monthly, what's our N? How many times per year is that? 12 times per year. So that's how many times they are calculating that interest for us. So divided by 12 raised to 12t. But then it gives us this other piece of information. How long will it take the investment to reach $2,000? What variable is that $2,000? That's our A. We want to know if we throw $1,000 into a savings account, how long is it going to take to reach $2,000? Now are we starting to see why this is important? Maybe someone in your family has started a college fund for you, or maybe you are starting a savings account right now trying to save up for a car or for, I don't know, a PS4 or whatever you kids are buying these days. So it's important to not only know what you want it to reach, but how long it's going to take to reach there. So let's say your parents are trying to save for college and they're like, wow, it's going to take us 50 years to save for our child's college. What does that tell them? 1, maybe you need to find a higher interest rate, or 2, maybe you need to put more in the account initially or be adding money into the account every subsequent year. That continually adding to a savings account or to like a mortgage payment, that's the type of stuff that we do in finite math. We do like 2 whole units, I think, on financial type stuff. Mortgages, sinking funds, all sorts of good stuff that you will probably have to deal with as an adult. So this kind of stuff is important. And it's like, okay, I see the buy-in now. So folks, that brings us to the crux of this problem. What are we trying to solve for? What variable? How long? T. And where is that T? It's in the exponent. And that brings us to what used to be the unsolvable problems of this chapter. How do we solve an exponential equation? How do I isolate t and get that out of the exponent? we try to get the same bases. Well, how many bases do I have? Well, this whole thing is kind of the base because it's tied to that exponent. So we want to try to isolate that base that has the exponent. Let's first go ahead and let's isolate the base first. Folks, what am I going to do to get rid of the 1,000? Because I can't distribute it in, so we have to divide it away. So this is joined by multiplication, so I'm going to divide both sides by 1,000. Goodbye. Hello. If I type this parentheses stuff in on my calculator, 1 plus 0.12 divided by 12. Whoops, I did divide by 2. Let's try that again. We get 1.01 raised to the 12t. So it's an exponential equation, and I've got two bases. Can I write 2 as a smaller base? That's a no. Can I write 1.01 as a smaller base? Or the better question is, can I rewrite 1.01 as base 2? No. So what do I do with an exponential equation where I can't get the same base? We log both sides. And therein lies the importance of logs because, again, with investments and figuring out how long is it going to take me to save this much money, or how long is it going to take for me to own my house, how much time do I have to save for my kids' college, being able to solve for this T is very, very important in the world of money. And that's why these logs were developed, not invented to make life harder, developed so that we could solve these unsolvable equations. So we are going to log both sides. So log of 2 equals log. All that stuff on the right. Log. Now, folks who were gone on Friday, you may be going, oh, I kind of remember doing this, but it's like, wait, why are we doing this again? What has this done for me? This makes the equation look more complicated, but what it allows me to do is take that exponent and move it out in front as a coefficient at ground level. Having that log there is the only thing that allows me to do that. So log 2 equals 12t log 1.01. And now it's time to isolate that t. What's joining t to all that stuff in the equation? We got multiplication, meow, and we got multiplication, meow. Now, personally, I like to just divide by the log stuff first. So I'm going to divide by log of 1.01 and log of 1.01. I would do this on my calculator first. So on calc, do that first. Now what I noticed is that some of my students in third block tried to make that simpler and say log of 2 over 1.01. These are two separate logs. We cannot condense those into one. If they're separated by subtraction, you can condense the answer parts. But these, we pretty much have to type it exactly as it's written. So this gets rid of that log over there. And then our step after that, divide by 12. So that dividing by 12, that's going to be our second step. So calculator time, log 2, close the parentheses, divided by log 1.01, close the parentheses, enter. Gross, we're not going to do any intermediate rounding. We're going to hit divided by, and that puts the answer in, that stored value, and divide it by 12. And that gives me, rounded to the hundredths place, we've got 5.80. 5 is enough to bump up that digit, so 5 bumps that up to be a 1. So 5.81 years. So that's how long it would take for the investment to grow by that amount. Any questions with that process? It's the same thing we were doing last week where it's like, oh my gosh, we can't get the same base. What do we do from here? But having that story problem or word problem component does take it up a slight notch. I think we're going to take a quick breather before we move on to the last problem, and then I want to talk about a few things in the homework. So if you've got to use the restroom, do so now.